Well, let's go through this exam. So question 1, which carbocation would not be likely to undergo rearrangement? Well, when we evaluate, that's a secondary, that's a primary, secondary, tertiary. Tertiary carbocations don't undergo rearrangement because they're already the most stable carbocation possible. Now, you can have tertiary carbocations rearrange to like benzylic tertiary carbocations because those are slightly more stable. But generally speaking, tertiary carbocations don't undergo rearrangement. So that would be the answer for question 1. What is the best description here? So in order to really answer this question, well, we need to figure out what the products look like. And so we would have one product that would add the chlorine to that carbon. And adding it to that carbon would add it in this way. We could add it as a wedged chlorine, and then that would make the methyl group a dash. Or you could have approached it from the other side, and the chlorine would have come in as the dash, and then you would have the wedged methyl right there. So those are the products that would form from that reaction. And so what do we have here? This would be a racemic mixture. Now, why are we getting a racemic mixture? Is because the first step in this reaction is the pi electrons here are the electron rich. So those are going to come in and do that. And when that does that, where's the proton going to go? Well, it's going to go to the carbon, or the carbon with the most hydrogens. And the two carbons of interest is that guy and that guy. Okay, so the hydrogen is going to go here, which leaves that with a carbocation on that carbon. And now the chloride can come in and attack from the front face or the back face. And that's why you are going to get a racemic mixture. So how many different E2 products can be obtained from 3-bromo, 3-methylpentane? Well, for this problem, it'd be a good idea to start off by drawing what that starting material looks like. And you would see that it looks like this. We could have Br and our methyl like that. Now, we understand that that's not a stereocenter. However, you still have to view it in the lens of the three-dimensional shape. Okay? Because you see here, it says an E2 mechanism. So we know we have to have the leaving group and the hydrogens antiperiplanar. So we just have to figure out which hydrogens there are that can be abstracted. And so we're going to have a hydrogen there and a hydrogen here. And yes, we still have the two hydrogens right there, but those are the same thing as the ones that I just drew, or the ones that are shown there. They're going to give you the same product because they're symmetry. And then we also have some hydrogens coming off of that methyl group. Well, that's a methyl. Sorry. And then we have 3 hydrogens coming off of that guy. And let's go 1, 2, 3. Just draw it like that. Okay. So we have the 2 blue hydrogens and the 3 black ones. And so if we grab one of the black hydrogens, we would have to make sure to give us a conformation that's antiperiplanar, but we would eventually come up with a product like that. So if we grab one of those hydrogens and make sure it's antiperiplanar to the bromine, we are going to get that product. So that's one. And if we grabbing one of those versus one of those, if we rotate around this bond right here to get those hydrogens anti-paraplanar, you're going to have two possible products. You will have one where you have the...
Finding the things you and your family need to be well is kind of a big deal. Finding ways to save on those things is an extra big deal. Check out extra big deals at CVS. Extra Care members get extra big savings on more of what matters most every 2 weeks. It doesn't get extra bigger than that. Shop tons of extra big deals at CVS today and come back for more every 2 weeks.
Say when.
Look like this. We could have the cis right there. And then we could, well, not cis, we would actually call that what? An E. And then you could also have this one, like that. And that would be the Z. So those are the three possible products that you would get for doing an E2 mechanism on that starting material right there. So the answer would be E for 3. Okay, so this problem right here, problem 4, predict the major products for the following reaction. Well, we need to remember that the alcohol is going to go to the more substituted carbon. And the bromine is going to go to the, so let's do it like this. So the alcohol is going to go to the more substituted carbon, and the bromine is going to go to the least substituted side. And if you look at the mechanism explains that regiochemistry. Now, how does the bromine and the alcohol get added? They get added in an anti-fashion. So we are immediately looking for, so in these problems right here, we see that the alcohol on all 4 answer choices are on the more substituted carbon. So that's good. And then we can clearly see that the bromine is all on the least substituted carbon. So then how could you tell what is the correct answer? Well, you have to remember this part right there, that the addition has to be anti. So that and that are both wedges. So that's sin. So that's off the table. Wedge dash, that's anti. So that's good. Dash dash, that's sin. That's out. Dash wedge, that's anti. And so the answer choices are 2 and 4. And so do we see that as an answer choice? Right there. Question 5. Zoom out a little there. So for question 5, this hydrogenation reaction here, we have to just remember how it occurs. So if we had something like this, we have a double bond there. Let's stick on an ethyl group there and isopropyl right there. Okay. The hydrogen's atoms, when they come and add to that double bond in an addition reaction, the hydrogens are going to add syn. They're going to add to the same face. So if the 2 hydrogens come in and add from the top face, like this, both on the same side, then that means the ethyl group is going to have to add on the back, and then the isopropyl also on the other side. So we see that we have syn addition because those 2 hydrogens are coming in on wedges or the same face. You could then see the alternative where the hydrogens come in from the back face. And so you would have wedges for the isopropyl. and wedges here for the ethyl. Okay, so that's the key feature of this reaction. So when you take a look at this one right here, it's going to add in a syn addition, but this one's a little bit tricky. And that is, when you take a look at this, does it get converted to that or that one and so forth? That's what we're looking at. But if we think about it backwards here, okay, so compound 1 had to come from a species that looks like this. Okay, just like that. That's the stereochemistry. Okay. And where's the hydrogens that are getting added? Well, we're adding one to that carbon and one to that carbon. So what we have is this guy went to that guy. Let's draw that a little better. Okay. Now, what compound would go to this guy? Well, if we just leave it like this, and we have our dashed isopropyl right there, that would go to that. But what is the relationship between those two compounds? Hopefully you see that those are enantiomers. So if this guy came from this guy, and this guy is an enantiomer to this, then that means then those species right there cannot be an option, because the starting material is this enantiomer, not this one. So right out of the gate, you can see that this cannot be an option because it comes from the wrong enantiomer. Okay, and same with that guy. Those two right there are going to come from the same molecule, that guy and that guy. So that was a trickier problem, because all 4 of those options are showing that the hydrogens come in on or add in a syn addition. And that's true, but we have to pay close attention on where those molecules are coming from. And those guys right there came from that enantiomer right there, which isn't an option because we only have one of them. Okay, let's see here. So what's the best way to achieve the following transformation? Well, what kind of product did we make? We made the Hoffman product. So in order to do that, we need a strong, bulky base, because we want to attack this hydrogen right here. And if we used a smaller base, it would have went for that guy to give us the thermodynamic product, which would be that guy. But we want to abstract this proton. And so if we use a bulkier base, it's going to prefer the less sterically hindered one. So answer E. Predict the major product of this reaction. The oxymercuration demercuration is a reaction in which you don't have carbocation rearrangements. And the alcohol that is being used is going to go to the carbon that's more substituted. Okay, why is that one more substituted? Well, this carbon over here has 2 hydrogens, and then this carbon right here, that one, has just 1 hydrogen. So it's going to go to the more substituted side, which means that carbon. Excuse me. So the ethanol is going to go to that carbon, which means that product. No carbocation rearrangements. Let's see, question 8. Predict the major product. In this one, the alcohol is going to go to the least substituted carbon. And the hydrogen is going to go to the more substituted carbon. And that's going to add in a syn addition. Okay. So where is the OH on the, so that's the least substituted carbon, the OH is there. That one also on the least. Okay. This one's off the table because we know that the hydroboration reaction gives us alcohols. So we have 4 options here. This one, E right there, is showing us, hey, the alcohol goes to the more substituted carbon. So we know that's off the table because the alcohol goes to the least substituted. Okay. And same with A. That goes to the least substituted one. So that one's off the table as well. Let's see here.
Shop bestsellers at Ashley, where no matter what your holiday traditions are, you're always at home. Whether you're making extra room with our extendable dining tables or creating the perfect cozy space with our modular seating, shop holiday deals and make lifelong memories with Ashley.
I think my pen just died. Let's see. And then it says it has to be syn. So that one's off the table. So now we're just down to 2, C and B. How did the alcohol and the hydrogen get added? So if we zoom in here, that's a dashed hydrogen. So that's a wedge, that's a dash, so that's anti-addition. And then this one is a wedged hydrogen, wedge, wedge, syn. So that's our answer. Okay, what are our nucleophiles? Well, the nitrogen species has a lone pair. That's nucleophilic. The oxygen atom has 2 lone pairs that can act as nucleophilic centers. And then we have a pi electron. Pi electrons that can act as a nucleophile. And so we've seen examples of addition reactions with pi bonds acting as nucleophiles or bases. And so the answer choice would be C. Number 10. Which of the following 2 compounds will undergo an E2 more rapidly? This one is a pretty cool problem. If you take a look at the chair conformations, if we take a look at compound 1, we'll put the tert-butyl there and then the chlorine there. When we draw the chair flip, okay, we're going to see this. Like that. But if we take a look at number 2, what we will see is this right here. An equilibrium. Something like that. Okay? Now, what's the requirement for an E2 reaction in a ring? Antiperiplanar. And in order for that to occur, the leaving group has to be in the axial position. So that's axial and that's axial. Okay. Now when we compare the red chair and the green chair, both the ones with the blue circle, between those, which one do you think would be the most stable? Well, in this red one, what do we have? We have both of the bigger substituents in the axial position, which makes it unstable in comparison to both bonds in the equatorial position. So this is the most stable of the red chairs. But in order for it to do a E2 reaction, it has to be in this conformation in the left, which is very unstable. When you compare the green chairs, we have this terp-butyl axial, this one equatorial, which is the best that it can do, right? This one's equatorial and this one's axial, okay? So when you compare the two green ones, the terp-butyl group is the biggest group, so you want that in the equatorial position. So the most stable chair for the green chairs would be this guy, which is the most stable between the two green ones. And because that's the most stable, and the chlorine is in a axial position, so now it can do a E2 reaction. And so when you compare this guy and this guy, you can clearly see that the green one is going to have the chlorine in the axial position, and it's the most stable chair. So that would undergo the reaction the fastest. And so that would leave us with answer choice D.
Here's to deserving more. More fangirling over sound you can feel. More wow. Love this look for you. More play. Tell mom it's tumble tested. More reason not to get up. More what? More mess-free. Hide pillows, snacks, up to you. Yup, more of this feeling behind everything we do. Because deserving more is deserving better. More style, more quality, more value. We are American Signature Furniture.
Question 11, which of the following statements about solvents shown below is true? Well, just remember, product solvents are molecules that have hydrogen atoms that are attached to fluorine, oxygen, or nitrogen. Hence, they can hydrogen bond. And so which ones can hydrogen bond here? That guy, and that guy. Because we see a hydrogen atom directly attached to a nitrogen or an oxygen. Okay. And so the others would be aprotic, which are molecules that have hydrogens, but they're attached to atoms other than those three. And when they're attached to other atoms, they don't undergo hydrogen bonding. So the correct answer choice then for that would be B. Okay. So 2, 4, and 6 are aprotic. Okay, 12. Which of the compounds undergoes the fastest SN2 reaction? Well, we know that a SN2 reaction happens in a concerted fashion, and so it has to come in backside attack. So when it comes into backside attack, it has to deal with the beta groups or the beta carbons. That's beta, that's alpha. There's our alpha carbon. The alpha carbon is the one that's directly attached to the leaving group. And so when that nucleophile or the hydroxide comes in, it has to deal with this beta carbon. And if there's a lot of steric bulk to that beta carbon, then it makes it harder to come in and do that backside attack. So you want the ones with so the best would be a methyl halide. That's the fastest, and then primary alkyl halides. Okay, so there's a methyl halide right there. That's primary, but with a bulky beta group. That's primary. This one's tertiary, so that cannot undergo SN2. That is secondary, and it can undergo SN2. And so what's the best one? The methyl, because it has the least steric bulk to it. Number 13, rank the following nucleophiles of increasing nucleophilicity. We're assuming, well, it's telling us that we're in aprotic solvents. So when we're using aprotic solvents, we can completely ignore that the solvent will interact with any meaningful significance with the nucleophiles. So we just look at these nucleophiles and look at their relative stabilities. And if we have stability right here, which ones are more stable? We have 3 energy spaces here. The neutral molecule water is going to be the most stable. And then you have to compare the stability of the OH minus versus a NH2 minus right there. And if we look at the periodic table, if we go carbon, nitrogen, oxygen, fluorine, when we compare the oxygen and the nitrogen, which one of those atoms can tolerate a negative charge the best? Well, the more electronegative atom, which is oxygen. So the OH can handle the negative charge a whole lot better. So that's going to be more stable than the nitrogen species charge. So that would mean that OH, or the hydroxide, is the next instability, and the NH2 minus is the least stable, which makes that the most reactive or the strongest nucleophile. So for problem 13, the answer would be C. Question 14, predict the major product of the following reaction here. Now, when we treat an alcohol with concentrated sulfuric acid, we are going to do this via E1 mechanism. And for us, in this problem, it told us which mechanism we're going to use. So the first step then would to take...
With the best Halloween decor from Michaels, we're not twinning. We're winning. Because Michaels has
the alcohol and grab a proton from the acid. So we can just draw it like this, a hydronium. That's going to come in and grab a proton and generate water there. Then we said it's an E1, so that means that the next step is that the leaving group has to leave. Okay, and what does that generate when that leaves? And generate a secondary carbocation. All right. After it generates a secondary carbocation, we have to ask, can we do a hydride shift? And yes, there's a hydrogen right here that we could do a hydride shift. Okay, and what does that do? It shifts the carbocation there, and now that's a tertiary carbocation. And so we have hydrogens here. That's beta to the carbocation. Here. And here. So which one would give us the more stable compound or the thermodynamic product? The answer being which alkene is the most substituted. If we grab this hydrogen right here, then we are going to get a product that puts the double bond in this position right there. Okay. So if I chose this proton, I would have got something that looked like that. If I chose that proton, I would get something like that. So when we compare those 3 that I've just highlighted, which one's more substituted when we're looking at the double bond? This one's a di-substituted. This one's a tri-substituted. And this one right here is a tetra. So that's the more substituted alkene. So that makes A the correct answer. All right. 15. What is the expected major product resulting from the following reactions? Well, obviously the first step would have to be, can we draw the starting material based off of the IUPAC name? And there's that molecule right there. That's how I drew it. And when we treat an alkene with hydronium, that's a hydration reaction. Where's the alcohol going to want to go? We have this carbon or that carbon. Well, it's going to go to the more substituted side because that would generate a more stable carbocation. And so 15 would be that right there. Okay, the free response questions here. So what is the major product of this E2 reaction? Well, we notice that we have a hydrogen right there on that beta carbon. And on that beta carbon, there's no hydrogens. So we are only worried about one hydrogen. So if I draw myself the Newman, okay, draw my eyeball going right through there and draw a Newman, the Newman will help me to orient where all these pieces are. Okay. Like that, and then we have the back carbon like this, and my methyl. Now what we have to do is realize that it's this hydrogen and that hydrogen are the same thing, and I need that antiperiplanar to the chlorine. So if I take the back carbon and rotate that, so I'm going to leave the front carbon alone. So that's going to stay the same. And then I'm going to make sure the hydrogen gets moved there. So where does that move all the other groups? It would move it like this. Okay. Now notice that this hydrogen and the leaving group are antiperiplanar. So we can do the reaction with relative ease. And so what is the relationship between that group and that group? Do you see they're on opposite sides of one another? And so that's the shortcut. When we draw our double bond like that, we know we have to have a tert-butyl, and that has to be on the opposite side of the methyl. And so if I've accounted for those two pieces right there, where would the ethyl and the hydrogen be? Those would have to be on this opposite sides as well. And you can see the ethyl right there and the hydrogen right there. And then this hydrogen and this chlorine right there are completely gone because they've been eliminated to form that double bond. So what we see here is a conformation that looks a little unsettling because we have a bulky tert-butyl group and a bulky ethyl group on the same side, giving us a Z isomer.
Get the new iPhone 17 Pro and iPad and Apple One, all for $0.
That's real nice.
And that is the only possible product that you can make, because that's the only conformation that you will find with this hydrogen and that leaving group right there, antiperiplanar. So if that's the molecule that you drew, then you got the full 8 points. If you drew this product right here, the E isomer, like this, okay, that's the E isomer, because that group and that group are on opposite sides of one another, you would get 4 points. But realizing that is not possible. Okay, so we have a so that's just only one product that's possible, and that would be this one for a total of 8 points. And that would be a example of a stereospecific reaction. Okay, question 17. So the correct answer would be 4R. We have a stereo center here. Like that. So the point breakdown right there, if you got the correct parent name right there, that's plus 2 points right there. So what would the, so 1, 2, 3, 4, 5, 6, 7, 8. Or you could have numbered it this way, 1, 2, 3, 4, 5, 6, 7, 8. And so what's the correct numbering scheme? That would be the red numbers because it gives the substituents the lowest locant number. Okay. And so if you got all that, where the substituents are and how to name them, you got a full point for that. And then if you figured out the stereochemistry, that stereo center right there is an R, that would be an additional point right there. So that's the four out of the 8 points possible for that question. And then the second half, if you drew this molecule right here, 1, 2, 3, 4, 5, 6, 7, like this, like that. Okay. And for this one, you got 2 points for the parent structure. You got 1 point for the substituents. And you got 1 point for that part right there, that it was trans. Okay, question 18. Question 18, the correct answer looks like this. That right there is a transition state. So you have to draw a transition state. So we have to imply that our transition state is flat, that the leaving group, which is the carbon-bromine bond right there, is leaving at the same time that the oxygen-carbon bond is forming. And because this is a transition state, we have to stick that into brackets. And then we do this double dagger symbol to illustrate the transition state. And then we also have to include the partial negatives on the nucleophile and on the leaving group. And so if you missed any of those parts that I've just drawn, you get minus 1 point. So for example, if you forgot to put the double dagger, that's -1. If you forgot to do the brackets, that's -1, and so forth. So that's what we are looking for that transition state. Okay, question 19, that's hyperconjugation. SN2. And for question 20, you have to do the mechanism here. Okay. I said that it's an SN1. And the way that this is going to do an SN1 is that we're going to have a alkyl shift at the same time we kind of kick off the leaving group type thing here, okay? So you could envision, if we drew it like this, you might envision something like this. The leaving group leaves, and then that turns into a primary carbocation. And then that primary carbocation does a 1,2 alkyl shift, right, like this. And the alkyl shift then would look like something like that. Now we have a tertiary carbocation right there that water can come in and attack. And then you would generate this product right here. And then you would do a proton transfer with some water to get our final product that looks like this. Okay. And that is the final product, and that is the full 8 points. Okay. That's what it's supposed to look like. Now, if that's the way you thought about it mechanistically, then there's a minor flaw in that. Even though you got to the right answer, looking at this right here, we have a primary carbocation. Primary carbocations don't form, okay? So the mechanism that we would invoke would be something like this, where we do a alkyl shift at the same time that we kick that leaving group off. Kind of happens in the same step there. And then we would get that species. And then we proceed by the mechanism that I just showed you with having water come in and attack. So you get a full 8 points for that species. If you did this as your product, okay, if this was what you drew as your product, like that, then you would get plus 4 points because you realized that it was a substitution. You just didn't do the rearrangement. Okay? So I hope that is helpful. And if you want to just see all the answers right there for the multiple choice, there they are.
Sure. We triple stitch each pair of bean boots and construct them with care up here in Maine. But this is when your bean boots become yours.
Walmart Plus in-home with Frankie. Hi, Frank. While you're away, a friendly Walmart Plus in-home associate could be delivering your orders free and putting them away inside your fridge.
Bye, Frankie.
Try a 30-day free trial.